The next speaker is Barbara Belvisi, CEO of Interstellar Lab, and they will be talking about sustainable space settlement.
Hi, I'm very happy to be with you today. So my name is Barbara. I'm the founder and CEO of a company called Interstellar Lab. And I'm going to tell you a bit more about what we're doing and the system we're building for the Earth, the Moon, and in the future Mars. Okay, so that's us. So we're a company, a American-French company actually, and we've been out there since September 2018. We're a team of 20 people, and we just opened our first facility to start the mounting of our first system. So very exciting time and a lot of updates since last year for those who've been watching my presentation last year already. So what we're doing, our job is to design and to build a deployable system. So we're working on inflatable structure that can help the human live in a more sustainable way, whether it's on Earth and in the future in space. So more specifically, what we've been working on for the past years is to develop environmentally controlled module where you control inside all the atmospheric condition, the humidity, the temperature, the O2, the CO2 level, and you can grow food and at the same time have a regenerative approach, a sustainable approach, where we can recycle the air, the water, and the waste. The first system that we've been designing is for terrestrial application, and our goal is to test on Earth and to develop system for Earth before we can develop a system for space, and it's going to be step by step. First, low Earth orbit, then a lunar station, and then Mars, that we see more in the 20 coming years. A little bit more about how we design our station. So it's called eBios, which stands for Experimental Bioregulative Station, and it's composed of several modules. Here you can see there is the tunnel module that is allowing us to connect one flower. This is what you can see right now on the screen to another one. You have 3 Biopod. I will explain a little bit more what they are about. Those are the structure you can see on the right with the transparent layer. At the center, you have a connector on which you can connect different pods and the different module. You have an entrance door, and you have the habitat section. And the habitat section, which is a combination of a 3D printed structure and a deployable inflatable structure inside. All the system has been designed to be completely modular, and they can work as standalone pods, but also plugged together. They form the station. So what was very important for us, and you can see here a fully plugged station. You can switch. You don't need to put a habitat section. You can decide to do only flowers with only greenhouses and our aeroponic system. It's a very modular system, and we're trying to recreate here redundancy because each pod is working by itself. So each pod has its water system, its atmospheric system, its control system, and of course, when you plug all the pods together, you have a kind of a network effect where we're trying to compensate the different level of O2, CO2, water with the connector at the center. But otherwise, we're recreating and we're separating all the pods because of course, if one system goes down, you don't want the entire station to be impacted. So each pod is really separated from the other in a sense that it works by itself, but connected by sharing the resources they can generate. So that's an overview of the experimental bioregulative station. So this one, we designed it for a group of 10 astronauts, and it's combining different, and it can support a group of 10 astronauts. I need to bring the food, the water. We have a waste treatment unit, and also we recreated a greenhouse. So that's an aeroponics unit, which is purely dedicated to food production. So we've been working on a couple of design iteration on the aeroponics system. So aeroponics, it's when you spray droplets of water at the roots of the plants. So we choose the system because it's very it consumes much less resources, much less water, and it goes directly into and the nutrient solution goes directly into the roots. And also most of the plants can grow actually in an aeroponic system. And it's allowing us to have different type of cultivation, whether it's purely vertical, horizontal, or what we call A-frame with a little slope. And so this section, this dome, is completely dedicated to food production. And here, the strategy, why we're also isolating one dome from the other, is because here we want to boost the level of CO2 in opposition with the habitat section, where you don't want to boost the level of CO2, obviously. The second unit is called the greenhouse unit, and this one is really designed to fulfill the physiological needs of human being, and also to grow some of the trees that can provide some fruits that we can't go in the aeroponic system. The treatment units, so as I said before, each unit works independently, so it has its own water treatment purification system, its own atmospheric system, but still there are some waste that we will not recycle at the unit level, and there is a dedicated unit for the human waste and for the organic waste as well. And so that's the treatment unit here, where we plugging in different system for the waste, the human and the black water that is not treated at the pod level. The habitat section I already told you about, which is a combination of a 3D printing structure and an inflatable dome in the middle, and the tunnel on the right side. Last year I presented for the first time what the code name was Baby Dome. Baby Dome was a smaller version of the Aeroponics dome. And since actually we presented the Baby Dome at the Mars Society last year, we received a lot of demands, and we changed a little bit our approach and our business model, and we've been working on the manufacturing of the Biopod. So we did a lot of iteration design to have a product that we can easily manufacture. So right now we are moving into a phase where we are finalizing the composite base. So as you can see in this picture, the Biopod is composed of a white composite base, and at the entrance an airlock and an inflatable membrane. So it's a completely air-supported structure, an inflatable membrane which is composed of two materials. And so this Biopod we're going to manufacture 2022. So the first one will be assembled in Paris. The initial plan was to assemble in the Mojave Desert, but we had to change a little bit our plan. But I'm very hopeful we're gonna bring the second one in California by 2022, by mid-2022. And so the Biopod it's a smaller version of the dome you've seen before. The Aeroponics dome, the greenhouse dome, they're pretty similar. And it's this one in terms of size. It's 11 meter long, 4.5 meter high, and 6 meter wide. And this one, we use material for terrestrial application. So this one will never work on the moon, and will never work on Mars. We will need to change the material system. Here we are using a PTFE and ETFE, and we have multi-layer with air chamber. What we're exploring for lunar and Martian application will be to have several layers, of course, of material, and including around 7 centimeters of air and 5 to 7 centimeters of water to try to recreate a shield that will protect from solar radiation. But we're not there yet. We have a whole plan of getting there. But the first idea with the Biopod was really to get a greenhouse here on Earth where we can test our automation system. So that's another render of the Biopod. It's gonna the first one is gonna look really like this. We're finalizing. We're working on the molding parts right now to assemble the composite base. So that's a view from the top. So we like a biomimicry. So you can see here a lot of inspiration from some insects and some different code and reference we've been taking from nature. And so inside the Biopod, we're combining aeroponics technology with greenhouse technology. If you don't want to have a greenhouse and you want to go full aeroponics, that's also something which is possible, because inside all the system is completely modular. That's another view from another angle. So at the entrance, you have an airlock with a double door, and we constantly maintain an overpressure inside the dome, as it's an inflatable dome, which creates a pathogen-free environment. And that's going to be, I mean, what is interesting is that this approach that we first started for space application, we discover actually there are there are a lot of right now application on Earth, and that's a system that is very sustainable for Earth. And so our vision for space deployment is really the inflation system before 3D printing. Right now, we don't believe 3D printing technology is stable enough to only rely on this for the first habitat structure. In our mind, it will go first with deployable system, and then we integrated with the integration of 3D printing technology. So the Biopod is completely deployable, modular, and using durable material. As I said, we have a composite base, and that is folded in that is cut actually in 5 pieces that you can fold and unfold. So that's for the deployability. And you have a membrane that we just blow air inside, and then we create a air-supported dome structure. The atmospheric system, the air system is fully controlled and fully autonomous, checking what's of course the level of a pressure and adjusting the pressure so we can maintain the structure up. Inside, so it's mostly inside the composite base where we put all the hardware system. So the water treatment system, the water treatment unit, the nutrient dosing system for the plants, all the atmospheric systems, so including AC, a CO2 scrubber, auto generator, and everything is automatized. And so that's the main part that we've been working on with our embedded system team and software team, is really putting a lot of sensors. And so we have a model of simulation of what's going to happen inside the Biopod. We have data from the sensors, and then we have the intelligence of the system, which is really inside the pod. And so it's fully autonomous. So when we design it, we will try to have system that doesn't need to be controlled by mission control, and that can be fully autonomous. And that's where we think there is a lot of innovation needed, and especially if you think about long-term space settlements. And so inside, we have advanced crop cultivation technology. So aeroponics, as I was saying before, you can also put a greenhouse, but a substrate-based greenhouse. But it's we're reworking, to be completely honest, we are reworking right now on the design of the greenhouse, because we might do a different version of the aeroponics system for small trees. The automation, so that's one part that we believe is super important, whether it's on Earth or in space. And before going to space and putting an automated system, we need to test one here. So that's what we do right now. So it's all about, of course, the control of temperature, the control of humidity, checking the water level in the tank, recapturing the water back in the environment of the dome, and checking the light intensity so we can turn on and off the LED depending on how much light the plant's been receiving. We have several software that we've been developing. I think last year also I was presenting for the first time the crop selector. The crop selector is the beta is online and live. You can try it. So crop selector is an algorithm where you enter the number of people you want to feed and how much of the nutritional needs you will cover. And our algorithm helps selecting plants and organizing the culture inside a biopod. So knowing how much space we have inside the biopod, it will define how many biopods you need to feed people, and then which crop, and it will do a calendar for more than a year. So we're planning in advance everything that you can grow inside. And so to make sure we meet the nutritional requirements every day on a daily basis, and those are very wide nutritional requirements here. We're not talking only about carbs or protein, but we're going very, very deep into potassium, sodium, and vitamin B3, B12, and all of those topics, and really organizing the schedule over time, which is not very easy to do. So we developed this what is called an organic algorithm that is helping us defining the schedule to feed all the astronauts. That's some of the, so we've been, interestingly, we've been doing not only food production for this one, but also we've been testing a lot on different crops, more specifically on flowers. So this is one of the flowers that we've been growing in the aeroponic system here at the lab in Paris. We've been testing vanilla, and it's been going very, very well. Vanilla do actually pretty well on the aeroponics condition. So of course, we're not going to feed astronauts with vanilla. This was for other application, terrestrial application. But yeah, if we can grow vanilla on the moon or on Mars, that would be pretty cool and actually pretty useful to have some taste in in your deserts. So that's some basis of we've been running some experiment on which structure and which I'm losing the name in English, but what we should use to keep the plant inside their little structure. Here you can see some of the algae roots of our system. Here much interesting roots as well. That's one of the prototype, very early prototype of the Biopod. So we call it Quark. Quark is an environmentally controlled pod. Inside we control the light, the humidity, the temperature, the CO2 level. So we have a bunch of sensors. Here you can see the two version of Quark, a different sensor. We're measuring everything and everything is fully automated. So we're using the Quarks to taste different species, to do kind of to look at how they are reacting under several conditions, to find what are the best environmental conditions for them to grow, the level of CO2, the nutrition solution, and also we're testing the sensor and the automation of the system. So that was a very good way for us to approach also the supplier assessments and we actually eliminated some companies that were not satisfied with their CO2 sensors. That's another plant we've been growing, and of course it's a smaller, not a souvenir, but clin d'oeil, we say a small link to the first flower that have been grown into space. We also actually working on having one of our Quark, but designed in another way, in a more rectangular, square way, and to ship that into space, into low Earth orbit in the 12 coming months. Nothing has been announced yet, but hopefully next year I will be able to share more information with you guys at the next Mars Society conference. That's a picture of our 3D model of a station, and the station I was presenting you at the beginning. This 3D model, we will put it in the Museum of Space at Le Bourget, next to Paris, under the space settlement section. And as I was saying, it's a very modular approach that we had for designing this station, and the design of the habitat section is going to change actually a lot, like the Biopod design change, but the habitat section is going to change pretty much. That's a view from the top, where you can see the different system. Here you can see the view on the aeroponic dome with the aeroponic and A-frame tower that we've been working on. The landscape is actually a Martian landscape, like a lunar landscape, but it's a Martian one. I have some connection problem apparently. Okay, and that's another simulation, another render that we did, imagining if we put our Biopod and our station on the moon. The station on the moon, as I said, there are a lot of iteration we'll need to do compared to the version of the Biopod that we have right now. The first one's going to be on the material system, where it's not going to be TFE and PTFE for sure, but it's going to be a multi-layer system, and as I said, with integrated air chamber and probably a water chamber as well. The transparent part for lunar application is it's not really relevant in terms of letting the light get in, because you don't get so much light on the moon, but it's more on the psychological side of having and offering a structure that is open to the sky and to outdoors for human living inside. So that's something we will really try to push, and to have this transparent layer. It's probably going to be smaller than what you can see on this picture right now, but this is something we don't want to let go. So we'll try to find a way. On the On the deployability, so that's actually a picture for a short movie that we did for the deployment of a station on Mars. Probably maybe next time I'll share with you the movie, the clip. And so as you can see, as I was telling you, you can connect different flowers all together. And so, and you don't need all the time to put a habitat section. I think here on this one, I can apply. Okay. I received some notification, but here on this one you can see, so we form two hexagons, but you can actually play much more, and you don't need an hexagon shape. You can keep on, you know, putting different pods all together and grow the full structure. And so it's to recreate this redundancy, and at the same time to have like separated station that can work standalone, but also plug together. So we have a smart way of managing the resources, but also we separate the system. So if one gets down, it doesn't jeopardize the entire structure. So yeah, thank you. It's time for Q&A. We have 10 minutes for Q&A, and I'm happy to answer your questions now.
Wonderful. Thank you very much, Barbara, for the presentation. We have a lot of interest and a lot of questions. So let's see. All right, so we start with a question from Amit. They say, how is the ground cleared to allow for an even surface, so no roots or no sharp rocks under the pod?
Sorry, I missed the beginning of the question.
How would the ground be cleared in order to allow for an even surface, so like a smooth surface, so no roots or sharp rocks?
Inside the biopod?
Outside the biopod. So how would, I guess, how would you make sure that the pod doesn't, that, for example, like no plants grow under the pod, or there's no sharp rocks?
It's completely sealed. It's completely sealed. So there is the full structure is a completely sealed. So there is no communication with the outside world and the inside world. So the plants can't grow out there. Yeah, I hope I'm answering the question.
Great. Yeah, I also think probably the question could be like, how do you make sure, or do you place the pods on a very even and smooth and stable surface? Is this part of a consideration when you do place the pod, that the surface is very stable and smooth?
Yes, but so actually the pod is on small feet that we can adjust. So depending on how the terrain is, we can adjust the positioning of the pod. So the purpose of the pod is actually not to have any foundation and not to do any work on the surface to be able to install it. So of course, if it's if it's, you know, very if the angle is not good, it's not going to be any way to install it. But otherwise, the purpose is really not to clean the surface before installing the pod.
Thank you. Next question comes from Thomas. They say, why isn't the structure fully inflatable? Wouldn't it be easier or cheaper to transport?
Yeah, it's a good question. So we're probably going to change a little bit the design for bigger domes. For this one, which is like 60 square meter on the ground, having a base, a composite base, it helps us, you know, get something that is a pretty heavy and solid, that is structural actually to the entire dome. And inside we have all the hardware system, and all the hardware system is pretty heavy. And so we decided to have this shell as a structure, as a base structure, and then the inflated dome on top of it. Right now, and we also need the connection with the door. So that's why we design it. But right now, what we think, and especially for much bigger dome, is that the airlock, will keep the airlock with part of a composite structure, the beginning of a composite structure, a composite base where we're gonna put all the hardware, but then all the pods gonna be inflated. So we're gonna reduce the rigid part of the pods. It's a good question.
Thank you. Next question is from Jody, and they say, what effect on plant growth do you think lower gravity will on Mars will have? Any plans or ways to test this?
So of course the first step for us will be to to leverage on all the experiment that has already been done in the International Space Station with for instance, the Veggie system of NASA. We have a roadmap where we want to send several species into space and to see how they're reacting. Yeah, we're pretty optimistic on the. I'm not a plant scientist. I'm not the. I'm not going to be very technical on this one. Some people in my team might better answer the question, but I'm pretty optimistic on the capabilities of plants to grow under low gravity environments, and we've seen that in the space station already. We've seen also that there are plants that develop interesting reaction into low gravity and create more molecule that can be very beneficial both for medical and pharmaceutical application. So we'll see how it goes. But for us in our roadmap before we go to Mars, the plan is to keep on launching a small structure into space and to see how plants are reacting and to test a lot of varieties of species. Then we will be able to answer, with more data and a more scientific approach this question.
Thanks. Next question from Dusty. They ask, where in the USA will you set up the biopods? Will it be a partnership with current analog programs, or will you do it on your own?
A partnership with who?
With current analog missions like Mars or B2 or MDRS?
Okay. Yes, it can be partnership with several structure. We're already talking to some of the people you just mentioned here. The first one, I still don't know where we're going to put it, whether it's California, Utah, Texas, Florida, we'll see. But it's going to be in collaboration. It's going to be, so we have customers, we have people who are buying the biopods that we're going to implement there. Yes, several options.
Great. Next question is about the application of the biopods here on Earth. So the question is, has the pods concept been considered for deployment in terrestrial applications as a response to the impact of climate change for agricultural production and for water management efficiencies?
Yes, yes, we're selling the pods at 200K on Earth, and we already have a 70 demand of pod, so which is a pretty good, even though we don't have our first pod full scale up and running, and the main application is a food production system, so sustainable food production system, because we're recycling a lot of the water, we use less energy, less resources that traditional indoor farming system. The second application on Earth is for the production of plants. So we're working with big brands like LVMH and some other famous fragrance and botanic ingredients companies that are interested in recreating specific climatic condition and to grow specific plants. So there are actually tons of terrestrial application. Other type of terrestrial application is for research and looking at how plants are reacting and playing with the different conditions. So it's really like a full, think of Biopod like a huge phytotron kind of, where you can grow whatever you want. But yes, it's right now the main application is for sustainable production of plants, for cosmetic and for food production.
Thank you. We have a lot more questions and 2 more minutes left. So let me ask one question that has been asked twice, and it is about the trees. So they say, both Nita and Jeffrey ask, what challenges do you anticipate in growing trees, such as walnuts? Is additional light provided?
Additional light, yes, I didn't mention that, but we have a different LED system, and of course we play with the spectrum depending on the type of plants that we're growing. Challenges with walnuts, I don't know yet because we haven't been growing walnuts in our system, a walnut tree. It might use a lot of water, but I think the main challenge with trees is actually how you maintain the structure. So aeroponic system is great for small plants and tomatoes and a lot of different like roots vegetables. But with trees there is this problem of having a structure that will hold it, because there is no soil, so you need to hold the tree. And this one we're gonna try different system, but it's a bit soon early for me to reply to this question.
Great. Well, thanks a lot, Barbara, for presentation and for answering the questions. And as always, we have a lot more interest here going in the Q&A panel. So if you have some time to answer, that would be amazing. Otherwise, we are looking forward to seeing all of your ideas come to fruition and thrive both on Earth and on Mars. Thank you.
Thank you so much.